Now in this lesson, we'll focus on influence lines for beams. This discussion will cover the influence line for shear and reactions, and then we'll just discuss the influence line for moments in another video. So in this problem, we have a simply supported beam, 10 meters long, so it's this span, and then it has an overhang of 2 meters at the left support, which is this one. Now we are to analyze this beam for the maximum shear at midspan, because as you can notice, the question here is the maximum positive shear at the midspan, as well as this one, and also this. Now first, we'll cover how the influence diagram must be formed. Now in forming the influence line diagram, we must place a unit load at important points along the span. Now these points include supports, or the point on the beam where you want to obtain the maximum shear or the maximum moment. And the next, we have to solve the reactions considering the placement of the unit load, and then we'll calculate the shear and moment at the point of interest. Now in many books, the location of the unit load is defined by a variable x. So let's say this is an arbitrary point of the unit load. We have x, and then this is 12 minus x. However, in this discussion, we'll just manually solve the reactions and shear values for the purpose of better understanding the lesson. Now just some reminder, for points where you are interested in shear, you should have two values, because we need to consider the left side and the right side. And so now, since we want the shear at the midspan, which is at point D, again, the midspan is only considering this simply supported span. That's why it's here and not at 6 meters. So that's also something you should remember. And so now, let's project a line from our important points. Now our important points are A, B, D, and C. And so we have this. And so let's move our load to the overhanging part, and then we'll solve the reactions as well as the shear or moment at the point of interest, which is D. Now just to reinforce the concept, the influence line defines the reaction, shear, or moment at a point at any given placement of a unit load. And so that means that when we are placing a load at the overhang, we are not calculating the shear at that point. Instead, when we place the load at the overhang, we want to know the shear that it will cause at D, because we are actually interested in the maximum shear at D for this particular problem. And so what we're gonna do first is we'll solve the reactions BY and CY. So we have BY right here, and then we have CY. And so to get BY, I can sum up moments about C. So I have minus 1 times the moment arm, which is 12, and then plus BY times the moment arm, which is 10. So times 10, and then this is equal to 0. Now again, this is taking moments about C. So BY will become 1.2 kN. Now let's just use 1.2 because this is actually unitless. So we have 1.2, and then to solve CY, we can sum up forces vertical. So summation of forces along Y, we have BY plus CY. Again, we'll equate the upward forces and downward forces as assumed. So upward equals downward, and then this is equal to 1 because this is our only downward force. And so solving CY, we know that this is 1.2, and so CY will be 1 minus 1.2, which is negative 0.2. And so that means that our assumption for the direction of CY is actually wrong. So this is actually downward. So this is downward, and then since we changed the direction, we will now use a positive sign. So this is 0.2. Now again, since we want the maximum shear at D, we can make a cut right here. Now recall that in revealing the internal forces in beams, the shear force will be downward at the left, while upward at the right side. So we have a downward shear force right here and upward right here. Now this is due to our sign convention. Recall that in shear and moment diagrams, these are our internal forces. Now this will be explained later why. Now let me just erase this one, and then we'll just actually consider the left part of our cut, and then we'll solve the shear force. And so considering the left side, we have minus 1, which is this force, and then plus 1.2, and then we have this downward shear force. So this is minus V, and then since we want to maintain equilibrium, this should be equal to 0. And so I can move negative V to the right. And so moving this to the right, we have negative 1 plus 1.2 is equal to V. Now this is the reason why we are using these internal forces, because we actually want to separate V so that we will know the sign of the shear. Because if we will use a downward direction, we can just move V directly to the right and then change its sign so that we will know the shear at that point. And so the shear at the midspan, when we have this load, is 0.2. Now again, this just comes from negative 1 plus 1.2. However, in the influence line, we'll not write this value right here. This is wrong. Instead, we'll place this value at the location of the unit load, and then we'll call that the ordinate. So this is the ordinate of the influence line at this specific point. And so what this means is we will start from 0 and then we'll now move up by 0.2. So this is 0.2 considering this value. And then you have to account the signs. If what you get here is negative, then it will actually move down. And then if positive, you will move up. And so this is our value. Now next, we'll move the unit load at the roller support. And so doing that, we have this. And so now, we need to solve the reactions first. So we have By right here, and then we have Cy. However, since the location of the unit load is directly over the support, then that means that By will actually carry all the loads. However, if I am to show that, we can take moments about C, and then we have minus 1 for this one times 10, and then plus By times 10 equals 0. We have By equal to 1. And so our Cy will become 0 if we'll sum up forces vertical. So this is 1, and this is 0. And so we'll calculate the shear at D. So we'll make a cut, and then this is the internal force, and we also have internal force here. And so solving the shear force, considering the left side, we have minus 1, and then plus 1 minus V is equal to 0. So since this just becomes 0, we have 0 is equal to V. And so the shear at the midspan, if the unit load is right here, is equal to 0. By the way, you can actually consider the left side or the right side, and then you'll just get the same value. Now if you'll consider the right side, we have summation of forces along Y. This will be upward, so that's plus V. And then we have no reaction at C. So this is plus 0, and that's equal to 0. So we have V equals 0. And so you can do this for the previous example. Just try to check for yourself. Now again, this is 0.2 right here. And then since we now know that the shear at the midspan is 0 when the unit load is at the roller support, then this is 0. And so what we're gonna do next is we'll connect the points by a line. So let's draw a line here, and then this is 0. Now for our next point, we will now move the unit load at D. And so we have this. Now again, this is 0.2, and then this is 0. And so now, we have to recall this concept. For points where you're interested in shear, you should have two values, considering the left side and the right side. Now what do I mean by this? In placing the unit load at D, we can actually make this cut. And then if we'll make that cut, then we can separate our beams into two. And so we have this. Now again, we just cut this section, and then we are now considering the left part and the right part. And so recall that from the left, we have a downward shear force. And then from the right, we have an upward shear force. These are our internal forces. And so we'll analyze this separately. Again, this is 0.2 right here, and then this is 0. And then let's first consider the left side of the cut. But we'll actually first solve the reactions. So going back, since this is only simply supported, then that means that the reaction here will be half of this load, which is 0.5, and also this one. Now you can still take moments about any point to get this value. However, since the location of the unit load is at the midspan, then our supports will equally share that load. So that's why this is 0.5. And so here, if this is 0.5, and this is also 0.5, then we can now solve the shear value. Now considering the left side, we have summation of forces along Y. We have plus 0.5, and then minus 1, and then minus V is equal to 0. And so moving V to the right, we have V is equal to 0.5 minus 1. And so our shear force at the midspan, considering the left side, will be negative 0.5. And so the ordinate at this point will be minus 0.5. So that will be right here. So let's draw a line. This is negative 0.5. Now, here at the right side, we'll get another shear value. So we have summation of forces along Y. We have plus V, and then minus 1 plus 0.5. This is equal to 0. And so our V will become 1 minus 0.5, which is equal to positive 0.5. And so at this point, the shear at the midspan will be positive 0.5. So this is 0.5, and then we'll just actually connect the two. And so once we connect them, we'll have this figure. This was minus 0.5, and this is 0.5. And so finally, we are now moving this load to the hinge support. And so by our concept, if the load is over the support, then our hinge support will carry all that load. So the reaction here at Cy will be equal to 1, while by will be equal to 0. And so solving the shear at D, we can again consider the left side or right side. However, I will just show you the right side. So we have our internal forces, this is V, and then upward right here. And so considering the right part of the section, we have plus V, and then minus 1 plus 1, that's equal to 0. And so V will become also 0 because this will just cancel. And so the ordinate at this point will be 0. And so let's connect a line. This will now be our influence line. And so now, we'll be able to calculate A, B, and C. And so let's just erase these. And then we'll now focus on our influence line. Now first, we have to determine the length of the beam where the uniform load could produce maximum positive shear at the midspan. Now how are we going to solve this? We'll just actually look at our influence line. Now notice here that these are actually positive ordinates. And so that means that when we'll place a uniform load at these spans, then we can produce the maximum positive shear. Now this is 5 meters and also this, since they are just half of tan. And so to produce maximum positive shear, we'll again consider these spans. Now the total length of these spans will be 2 meters plus 5 meters. So this is 2m plus 5m, which will give us 7 meters. And so this is our answer. Now what if, sir, I am asked to determine the length of the beam where the uniform load could produce maximum negative shear at the midspan? Now your answer for that will be this span, because this is the only span that contains negative ordinates. And so just an additional input for maximum negative shear at the midspan, we have 5 meters. This is the length of the beam where the uniform load could produce maximum negative shear at the midspan. Now for the next question, if the concentrated load alone is placed at the end of the overhang, we have to compute the maximum shear at the midspan. Now again, since the influence line defines the shear at a point at any placement of the unit load, then we'll actually place the concentrated load at the end of the overhang. Now this is 116 kN, and so we'll place 116 right here since it's at the end of the overhang. So 116 kN. And then to compute the maximum shear at the midspan, we'll just multiply this load by the ordinate. So we have V is equal to V at midspan is 116 multiplied by 0.2. And so this will give us 23.2, and then this is Kn. Now for the last question, this is independent of our above statements. Now if a standard truck load consists of two moving loads, 42.4 Kn and 35.6 Kn, and 4.3 meters apart, we have to calculate the maximum shear at the midspan. Now if we want to know where we want to place these loads, then we'll just check our influence line diagram. Now we know that 0.5 is larger than 0.2, and so that means that we can place our moving loads where the ordinate is largest. Now this is 0.5 and this is also 0.5, so we have two possible ways. However, for the purpose of simplification, we'll just say that this is the maximum positive shear, so that our solution will be exclusive to this. So if we are looking for the maximum positive shear, we need to place our loads at these points. Now these moving loads are separated by a distance of 4.3 meters. So this is 4.3, and then this is what we have to remember. The higher ordinate should contain the larger load. And so since the larger load is 42.4, then we'll place that at 0.5. So this is 42.4 kN, and then this will be 35.6. Now if let's say this is 54 kN, then you'll place 54 kN at this point because this will now become the larger load. Again, just remember this concept. And so we have this. So to calculate the shear at the midspan, we have 42.4 multiplied by the ordinate, which is 0.5. So times 0.5, and then plus 35.6 times the ordinate. However, since we still don't know that, we'll just actually use ratio and proportion. And so we'll solve this value. And now, we'll just make this more realistic. Let's move this, because this is 4.3 meters. That's actually somewhere here. So this is 35.6. And then this is the ordinate. So let's label this as y. Now, if this is 4.3 meters, then this is 5 minus 4.3, which is 0.7. And so using ratio and proportion, we have the whole triangle has a height of 0.5, so we have 0.5 is to 5 meters. That's equal to y is 2.7 meters. So over 0.7, our y will be 0.07. And so this is times 0.07, and then this will give us 23.692. And then this is Kn. And so this is our answer. And so just an additional input to make our discussion more holistic, let's say we are to find the maximum negative shear at the midspan, considering the highway uniform load and the concentrated load. Now this is our highway uniform load, while this is our concentrated load. And so to compute the maximum negative shear at the midspan, we'll actually consider this portion because we want the negative shear. And then since the ordinates right here are negative, then placing our loads right there will produce negative shear. And so we'll place our uniform load, which is 9.35 kN per m. And then since we have a concentrated load, we will actually place that at the higher ordinate. We will not place that here because the ordinate at B will be 0. And so we'll instead place this at 0.5. So we'll move this. Let's place that here. This is 116 kN. And so the shear at the midspan will be 116. Let's first consider this. 116 times minus 0.5. And then we have minus 9.35 multiplied by this area. Now we are multiplying by the area because we actually have infinite ordinates along the span. Again, this is only the concept, so we'll multiply this by the area. So we have minus 9.35 times 1/2 times the base, which is again, this is 5 meters, and also this one, so 1/2 times 5, and then multiplied by the height, which is 0.5. And so we can now solve the maximum negative shear at the midspan, considering the highway lane load and the concentrated load. So this will give us, by the way, this is minus because this is below the 0 line, and then all the ordinates are negative. Now this is 69.6875, and then minus, and our unit is kN, and so this is our answer. Now if you want to see this in action, let's actually model our beam. Now we know that for the maximum negative shear at the midspan, considering the highway uniform load and the concentrated load, we can obtain a value of minus 69.6875. And so our beam length is 10 plus 2, which is 12 meters. And so we'll change our length. This is 12 meters. And then we'll now place our supports. Now at 2 meters from the left end, we have a roller support. So this is the roller support. And then at the right end, we have a hinge support. So let's add a hinge. And then we'll now place our loads. Now we have 9.35 kilonewton per meter acting from B up to D. So that will be at the roller support. And then the span will be 5 meters because this is actually 5. Now since it's difficult to modify the values of the load if it's in kilonewton per meter, let's just use newton per meter because that will just give us the same value but with different units. And so let's modify this. Let's make this newton. Now we have minus 9.35 for both of these loads because this is downward. So this is 9.35, and also this one. This is minus 9.35. Now since this can't be exact, we'll just approximate this. So this is 9.35, and then it acts from B to D. So we have 2 meters, and then this is 5 meters. And then we have a concentrated load of 116 kN acting at 7 meters from the left end. So that's why this is 7. And so the value will be minus 116. And so if we'll calculate the shear at the midspan, we'll have this value. This is 69.7, which is actually equal to this. Now, let's try to move our load just a bit to the right. For example, let's move the distributed load by, let's say, 0.2 meters. The shear will now change. It will become minus 68.8. And then if I'll move it 0.2 meters to the right, again, this was initially 5. Then the shear at the midspan will be minus 68.8. And so notice that we can actually get the maximum shear, the maximum negative shear at the midspan only when the distributed load is loaded at this whole span. If, let's say, we'll move this back to 5, and then we'll move this slightly to the left, then the shear at the midspan will change. It will become minus 69.6, which is lesser than this value. And so that's why for the maximum negative shear at the midspan, we need to follow the influence line. So moving this back, we have 69.7 as the maximum shear. Now for the other loadings, let's say for this question, if the concentrated load alone is placed at the end of the overhang, compute the maximum shear at the midspan. So let's remove this, and then we'll place this load at the overhang. And then let's try to see what the shear in the midspan is. Now, as you can see here, if we'll go to 7 meters, the shear at the midspan will be 23.2, which is equal to this, 23.2. And then notice that the shear from this point up to this point is just actually constant. But this is still the maximum shear at the midspan. Now for the maximum shear at midspan, considering the truck load, let's place two loads, 42.4 and Let's just use 42 because it can't be changed. And then we have 35.6. Now let me just modify this. Let's make this exact. So minus 42.4. And then we'll now move this load according to this configuration. Now let's move it here. Now we know that we need to apply this at this point for the maximum positive shear. So this is at 7 meters from the left end, and this is 0.7 meters from the right end. So we have 42.4 at 7 meters from the left end. And then 35.6 is 0.7 meters from the right end. So this is 0.7. And so if you are to solve the shear at the midspan, it will be for the maximum positive shear, we have 23.692, which is this value. This is 23.7. That's how you can check. Now, if let's say we'll move this slightly to the right, let's make this, let's just say 6.5. And then if this is 6.5, since these two loads are separated by 4.3 meters, then this will be 12 minus 6.5. And then minus 4.3. This is 1.2 from the right end. So 1.2. And so notice that the shear at the midspan, which is at 7 meters, it will now decrease. It will become 14.8. And then it's actually negative because the location of these loads will touch this part, which has negative shear. And so I hope this simulation has helped you understand the fundamental concept of influence lines. And so you can try this app so that you'll better understand the locations of your loads. You can use this for other examples. Now, just another input, we know that if we'll apply forces at the overhang, then the shear at the midspan will be positive because this has positive ordinates right here. And so if I will extend this up to 2 meters, the shear at the midspan must be positive. That's why this is positive. Now, if I will move this load from B to D, then the shear at the midspan must be negative because this has negative ordinates right here. So let's move this to 2 meters and then up to 5 meters. As you can see, the shear at the midspan will be minus. Now, if we'll move the load from 7 meters up to the right end, then the shear at the midspan must be positive because this has positive ordinates right here. So let's move this. This is now at the right end, and then this is 5. Notice that the shear at the midspan will now again become positive because we are now placing the distributed load at a point where the ordinates are positive. So this is to reinforce the concept. And so now, we'll move on to the influence line of reactions. Now here, we are to find the maximum ordinate of the influence line for the maximum reaction at the left support. And so what we are trying to define is the influence line for the reaction at B. And so first, let's place our unit load at the overhang. So taking moments about C, I can get By. So I have minus 1 times the moment arm, which is 12, and then plus By multiplied by 10. This is equal to 0. And so the reaction at B, when the unit load is at the end of the overhang, that will be 1.2. So By equals 1.2. And so that means that this is the ordinate of the influence line. So this is 1.2 right here. Now again, we are not interested anymore in the shear at the midspan. We are only interested in the reaction. And so that's why this reaction at By is automatically our ordinate. So this is what you have to remember. And so now, let's move our load to the roller support. Now, if the location of the load is right here, then By will automatically become 1. Again, we have solved this earlier. This is directly over the support. And so, when the unit load is at the roller support, the reaction will be 1. And so, this is the ordinate of our influence line at this specific point. So, this is 1. And then, we'll draw a connecting line. And so now, since we are not interested in the shear, then we'll just actually move our load to the final point, which is our right end. And so, we have this. Now this is again 1.2 and this is 1. And then if our unit load is right here, then we need to solve the reaction of B. Now we know that if the unit load is directly over the support at C, then only C will carry that load. So Cy will be 1 and then By will become 0. Now again, we have also solved this earlier. And so this means that when the unit load is at C, the reaction at B is equal to 0. And so this is our ordinate. So this is 0 right here. And then we'll just connect it with the line. This is now our influence line for the maximum reaction at the left support. Now the first question is to find the maximum ordinate of the influence line. And so that's clearly 1.2. So for letter A, we have 1.2. And then for letter B, we have to find the maximum reaction at the left support due to the concentrated load. And so what we will do here is we'll place the concentrated load on the point at which the ordinate is maximum. Now since the ordinate is maximum at the end of the overhang, then we'll place the load there. So we have 116 kN, and then the maximum reaction of B will be, let's just say RB max. That will be 116 times 1.2, which will give us 139.2, and then Kn. Now if we will try to model this, we'll actually have this. Let's remove this load, and then let's place a concentrated load of 116 Kn, and then we'll place it at the end of the overhang. So this is 116, and then notice that the reaction at the support will become 139, which is the same as our answer. Now again, we had 139.2. Now if we'll move the concentrated load at any point along the span, then the reaction here must decrease according to our influence line, because it's actually decreasing here. And so if we'll move this directly over the support, then we have a reaction of 116 Kn. Now if we are to relate that here, the ordinate at this point is 1, and so 1 times 116, that will give us 116 if the load is over the support. And then if we'll move this to the rightmost end, then the reaction here must be 0, because the ordinate here is actually 0. And so this pretty much sums up everything you need to know about the influence line for shear and reactions. Now there's actually a shortcut for influence lines, and then what I will teach you now is the shortcuts for shear and reactions. Now let's say we want to draw the influence line for the shear at the midspan, which is at D. Now since we know that our internal force at the left is downward and then at the right is upward, then that means that we'll go down here and then here we'll move up. Now we know that this is 5 meters and also this one. Now the value of the ordinate at these points will be, for this side, this is, let's say, A, and then this is B. Now let's just use another color. For the influence line, let's just use purple. So we have a certain height here, again for the upward, and then from the left we have downward. Now the value of the ordinate here will be this distance divided by A plus B. Or simply, this is A over L. If we'll just consider the span. Again, you'll only consider what's simply supported. And so when getting A, you're not measuring it from here. Instead, you're measuring it from the roller support, because the influence line at this point will actually be 0 because we have a support right there. But let's just use A over A plus B so that it will be more intuitive. And then here at the top, by the way, we are using A because it's on this side. And then for this upward ordinate, it's for the right side. And so since on the right side we have B, this ordinate will be B over A plus B. However, take note that this is negative because it's below the 0 line. And so if you'll calculate this, we have our B is equal to 5, and then our A is equal to 5. So this is 5 plus 5. And so we have 1/2, which is 0.5, which is the same as our diagram earlier. And then here we have minus 5 because this is our A. And then over 5 plus 5. So this is also 1/2, but negative. And so these are our ordinates. Now once you have these, you'll now draw a line connecting to C. So from here, since this is for the right side, we will now go down, and then this will be 0 right here, because when the unit load is over the support, then we won't have a shear value at D. And then for the left side, we have going to the roller support, it will become 0. And then once you get to this point, since the relationship is just linear, you can just extend this line, and then this line has the same slope as this one. And so this will be our ordinate. Now let's say this is Y. Now to get Y, using this value, we can just use ratio and proportion, because the slope of these triangles are the same. So we have Y is to 2, considering this triangle, and then considering this triangle, we have 0.5 is to 5. And so solving Y, we have 0.5 times 2 divided by 5. That will give us 0.2, which is the same as our answer earlier. So this is 0.2. So this is the shortcut for shear. Now let's say we have this beam, and then it's simply supported, and then we want to draw the influence line at this point, for the shear at that point. Let's say this is 2 meters, this is A, this is B, and this is C, and then this is, let's say, 7 meters. Then our influence line will be here. We will go down, and we will also go up. Now this ordinate will be, this will be A, and this will be B. So this is A over A plus B, which is 2 over 2 plus 7. So this is 2 over 9. And then for the ordinate at this point, we have b over a plus b, which is 7 over 2 plus 7, which is 7 over 9. And so these are our ordinates. And then here at the supports, we'll go back to 0. So let's draw a line from here up to b, and also here. And so this is our shortcut. Now if you want to check this for yourself, try to solve this using the actual method. Now for the reactions, the shortcut is just to draw the ordinate of the support automatically. Now let's say we'll consider this again. So we have 2 meters, and then this is B, this is A, and then this is C. We have a roller support here, and then a hinge support at C. Then if we are to draw the influence line for the reaction at the roller support, we can just automatically draw the ordinate, which will be upward. And then this value will always be 1, depending on the support you're considering. And so once you have this, you will just connect a line up to the hinge. And then here, the slope will still be the same. And then we can draw this line. And then this is the ordinate for point A. Now again, this is 10 meters. Now we know that this is supposed to be 1.2, according to what we have solved earlier. And so let's say we still don't know this. Let's just use the value we have determined, which is at the support. It will move up by 1. So using ratio and proportion, we have 1 is to 10 for this triangle. And then that's equal to y is to 12. So y over 12. And so our y will become 1.2. So this is 1.2. And so just to reiterate, for the influence line at any reaction, move by 1 upward for the ordinate at the support you are considering. And so for the same beam, if let's say we'll consider the influence line for cy, we have this reaction. So this is cy, and then since we are considering this reaction, we'll move up at C by 1. And so this is the ordinate at C. And then we'll extend the line. It will become 0 at the roller support, and then the slope will still be the same. So if we'll extend this, this will now be the ordinate at A. Now to solve this, we can use ratio and proportion. We have, for this triangle, 1 is to 10. This is the height over the horizontal distance, and then that's equal to, let's say this is y. Y is to 2 meters. So our y will be 0.2. And so this is how we can get the ordinates. And so this is the influence line for cy, or the reaction at C. And so these are the things that you have to remember.